All right, so this is the linear momentum at T1. The linear momentum at T2, okay, let me go back to this picture here. Now, imagine what's happening. B is going off in this direction. A is going off in this direction. When the cord becomes taut, where is D?
In the middle of A and B?
Yeah, it's going to be the middle. It's going to be the mass center. So, and I'm going to make a little bit note. Note, at this point, because I'm going to use this idea, the ring D is at the mass center of the system of A and B. Okay, not C. C is not of concern to me anymore. C is gone. I'm just looking at the system A and B. I should have said that somewhere. Because that's all I calculated here for the linear momentum. I'm just looking at A and B. So let's stick it over here. Just considering system of A and B after cord is cut. Okay, so all of this is still true. It's just I'm being explicit that I'm only considering the system of A and B. Linear momentum's conserved, angular momentum's conserved, and I'm identifying exactly what I mean by T1, exactly what I mean by T2, and now I'm actually plugging into these equations and calculating. Okay, L1 is this. L2, okay, so now I'm going to use that alternate definition for calculating, or formula for calculating the linear momentums. This one, I just did it, just summed up the linear momentum of all the individual particles in the system, but this time I'm going to take the linear momentum, I'll calculate it by taking the total mass of the system times the velocity of the mass center. That's the second way we can do it. So in that case, it would be 2m, and then VD is exactly what I'm looking for. D is the mass center now. So there's and it's, how do I get the negative sign? No, I'll just call it, I don't know what VD is. I do know it's going down, but I'll just call it VD. So equating this with this, we will get VD is equal to minus V0 cosine theta in the j direction. So 30 degrees is 0.866, so that's the answer. The velocity of the first part here. VD is minus 0.866 cosine theta in the j direction. Okay, we're going to get these terms by doing the exact same thing, except instead of linear momentum, we'll do it for the angular momentum. And the first calculation for angular momentum at time 1 will be kind of similar here. We'll just get we'll add up the angular momentum of the individual particles. And then the second calculation of angular momentum, we'll use that alternate formula that basically gives it in terms of like the total angular momentum with respect to the mass center, with respect to the mass center, the whole system. We can get that from the chart, but I guess everything here applies. I'm just going to go ahead and erase it all, because you have it written down, right?
What would be the motion like after the cord is cut and the string becomes taut? Is it going to be spinning and moving at the same time? Like a bola?
Yes. Yeah.
Oh, it is
So,
like a bola.
yeah.
Okay.
All right. So we want to calculate the angular momentum of the system at time 1, the angular momentum of the system at time 2. And I just realized that I made a huge mistake in the way I wrote down that formula. you have it written, if you copied it, I hope you correct it. Because I just realized that just like a moment, you should never write it without a subscript that identifies the point that you're calculating moments about. You should learn that in statics, right? Well, this is angular momentum. It's the moment of linear momentum. So you have to identify a point that you're considering the angular momentum about. And I didn't in my formula. It doesn't matter what point you choose, but you better choose a point. So I think my formula, I had it like this. But I should have identified a point. Maybe I'll just go ahead and identify the mass center. Whoops. Okay, but you should never think about moments, whether they're the moment of a force or the moment of linear momentum, which angular momentum is. Never consider any moment unless you identify the point that you're considering the moment about. So my apologies for that. I caught it. So I'm going to choose to do the mass center. All right, so in my original system here, at T1, just after it's cut, here is the mass center. Here, this is the G at time 1. So let's see. Well, okay, what's angular momentum? It's R cross mv, right? That's the general formula. So we've got two particles here, so we'd want, the R cross mv for particle A, and then R cross mv for particle B. So there's R, right? And what is it? It's L sine 30.
Velocity is not perpendicular to the
Right, so I also have to, so I better do V0 sine 30. Is that right? So I'm just getting the magnitude here because the vector is going to be in the k direction, right? Because if this is R cross mv, I'll just stick a K here to make it, Oh, very important, by the way. It drives me nuts when students do stuff like that.
Huh.
Do you see the problem?
Yeah.
Okay, this is a vector, this is a scalar. You can't have a vector equal a scalar. So the magnitude of the vector is this and the direction is K, right? R cross mv. I forgot the M. I forgot the M. Sorry. Now I think this is good. Well, and I'm only halfway done, right? Because that's only for the A. Particle A. B is going to be the same, right? R is going to be L sine 30. And then the component perpendicular to R is V sine 30. It doesn't look like it there, but it is. Anyway, so it's actually going to be twice this. Okay, some of you look lost. Should I back up?
Oh, G is in the middle of A and B.
Right, because I'm taking the angular momentum about the mass center. And at time 1, the mass center is right here. That's why I have a subscript 1 here, because the mass center is going to be traveling. Well, the mass center is actually going to equal D in the second position. I guess it doesn't really make a big difference, but anyway, that's why I put the subscript 1 on it. So is everybody following how I'm getting that calculation for the angular momentum about point G, which is the mass center, at time 1? So I'm taking R cross mv. So R is this length here, which is L sine 30. Cross means that I need the perpendicular component of V0. In other words, the component perpendicular to R, which is V0 sine 30. Yeah, my picture is kind of weird. This actually should be perpendicular to that. So, I mean, if you drew it more carefully, but it does work out.
What's the angle?
Wouldn't it be easier?
Well, the angle is 30 because look, this is perpendicular to this. This is perpendicular to this. So this angle is 30 here, which means that this angle is 30
Shouldn't be the
here.
opposite? Shouldn't be 60 on the top? Because they are perpendicular?
This is perpendicular to
Yeah,
this.
so
This is
60 on the top, 30 on the
This
bottom.
is perpendicular to this. This, oh, you're right. So this is 30. Okay. So, and that makes it V0 sine 30. Yeah, I hate these details on the board. I'm sorry, but you can. I think you should be able to verify that it is sine 30. Well, we just did. Okay, so now, we're almost done. We've got the calculation of the angular momentum at time 2. Okay, so I'm gonna sketch that. You know, at that point, the chord is taut. I'm not even sure how A and B are gonna look, but you know it's gonna be a straight line. You know, this might even be B, A. And we do know that it's gonna be
It's like a couple.
Spinning.
So, and G will actually be the ring now. Okay.